All right. Good afternoon, everybody. Welcome to Science Sunday. This is my first Science Sunday of the season. And how many years have we been doing this, Mike?
Oh, boy. I think it's starting our 9th year now.
Yeah, your 9th year, my 7th year, something like that, right?
We brought you in and let you step in and switch hit a few times and stuff.
Yeah, this has been phenomenally beneficial to my life. I hope it has enriched your lives as well. Welcome. This is hosted here in the DuPage Unitarian Universalist Church, and it's sponsored by the Prairie State Humanists as well as the church and the American Humanists Association, for whom science is a critical and key part of our worldview and philosophy. For the Unitarian Universalist denomination in general, one of the things that is emphasized typically and habitually is the interconnected web of existence. And really, you can't get much more intertwined and interconnected than our relationship to the weather and climate, which is what we're going to be talking about today. So, so I hope that this is informative for you. It's really difficult to boil down really just a tremendous amount of information into an hour-long presentation. So there'll be some things that I skim over, some things that I will leave out, but we hopefully will have a little time for question and answer at the end. So let's get started without any further ado. So the slides are up, and hopefully you can see them. So I want to talk a little bit about our beautiful planet and our relationship to the atmosphere of our planet, and specifically some of the interesting behavior that our atmosphere exhibits. Some of this behavior is habitual. It happens again and again, season to season, year to year, with gradual changes. Sometimes the changes are relatively random, as you would expect for such a chaotic system, and sometimes the changes are predictable, like the change of the seasons that go from summer to winter, etc. So
it's going to get colder out, I believe.
You've been paying attention to the climate. That's good. Yeah, that's a safe bet that it will get colder here at our latitude. And we'll talk a little bit about why that happens. In fact, let's talk about the source, the driving energetic source of our climate, which is not the inherent heat of the Earth, as you might think, but it's actually the radiant heat of our sun. So this is a picture of our sun in, I believe it's hydrogen alpha light, so it emphasizes some of the sort of topographic features of the sun. Those are bright areas, or perhaps coronal mass ejections, and then we've got sunspots and granules and whatnot. But this giant ball of glowing nuclear plasma that's 93 million miles away typically is the source of the energy that drives our climate. And the light comes into our planet. For those of you that may be new to the ideas of science, our planet is round. I don't know, this may be breaking news for some. There's all sorts of lines of converging evidence that shows and proves, really, that our Earth is round, one of which is actually our climate and the climate cycles. And we'll talk a little bit about how the climate is a direct consequence of the round Earth. Now, one of the things that's true about our Earth being round is that the radiance, the flux of energy that we get from our star, the sun, is uneven from the equator to the poles. So you can think about this in terms of incoming light rays. If I've got a tube of light rays and they're coming toward a flat surface, then they hit, straight on. But as I curve up along the surface of the Earth towards the poles, well, this tube of light rays now makes a glancing blow against the polar regions of the planet. And the implication of that is that the equator, or the equatorial zone of our planet, gets more radiation flux, more energy input than the polar regions. And this is a critical factor in driving the engine of our climate. And before I go on, though, we're going to have to hit the books a little bit. I hope you're comfortable with this on a Sunday afternoon. But we're going to have to hit the books. We're going to have to pull out an equation. But we've got somebody here to help us with the equation. If I can ask him to make an appearance. All right. Looks like the animation isn't working on this version of PowerPoint. But hiding behind that bookshelf is an old friend of ours, Albert Einstein, who's a master of equations. But anyway, here's the equation that Albert would present to us. Big P is proportional, that's a little wiggly sign, is proportional to rho, that's the Greek letter rho, times T. That's your equation. Even simpler than E equals mc squared. What are these symbols? We've got big P, that's pressure. T is temperature. And rho is density. So this is a gas law. This relates the pressure and temperature of a gas to one another. And in order to make it an actual law of nature using some kind of cockamamie, maybe human-invented units, we have to put in a constant. And this constant we introduce because of human-created units. So I'm getting a signal. I've got a little technical error here on the Zoom meeting. Can I do anything to help? Okay. What's not happening correctly? Pardon me just a second.
Zoom has crashed, the video is not outputting, and the microphone is disconnected.
Okay.
Other than that, it's working fine.
Okay, other than the microphone and the video not working,
And Zoom having crashed.
then let's just get rid of this part because we've got plenty of cable here. So you get to see a technical demonstration of some AV equipment here. So we'll do this, and we'll unplug and replug this in. This is our power. This is power. So unplugging, plug the power back in, and now it should be okay.
We log back in.
Yeah,
That's what I do.
as our friend. It's the default. If you go to the website, you will log in, and one of the options that pops up there is the owner of the account. If you just go to the website for Zoom. Okay, so hopefully we'll be back online soon with our Zoom. Anyway, this is the only equation that we will use today. It relates pressure to temperature. And why is this important? Well, one of the facts about living at the bottom of an ocean of air on our planet is that the ocean of air is compressed near the surface because all of the other air is on top of it. So the pressure of the air near the surface of the earth is higher than the pressure higher up in the atmosphere. So as pressure changes, temperature changes. If you take a given parcel of gas, then change its pressure, then its temperature will also change. And we'll talk about that in more detail in a few minutes. All right, let me help again with the Zoom meeting. What's going on?
I remember we talked about the ocean of air a few Science Sundays ago when we were still meeting in the other room, and talked about that, and we talked about the pressure that builds down, that goes onto your hands and so on, that we're fighting against pressure that we don't realize. We're so acclimated to it that we don't even realize that we're fighting under, resisting to, and resisting from this pressure of air. We talked about how you'd realize when you went down to the bottom of the ocean, which is the surface of the land at the bottom of the ocean there, that we wouldn't be able to withstand those types of pressures here either. But it is interesting to realize that we're feeling like we're floating around with no weights and no pressures upon us at all. But they're here and evident, and we're just so we're born into this system, obviously, and we're so acclimated to it that it feels very comfortable in the system we're at, just like creatures that are down at the bottom of the ocean are acclimated to the pressures that are down there as well, too.
Thank you very much for pinch hitting for me,
Okay.
Mike. Looks like the Zoom meeting is having a problem. I did send out a notification to people that included both the Zoom link and the YouTube link for the church.
And if you go to DuPage Unitarian Church and just scroll down there, there's just a YouTube signal
Right.
that you can just click on and
Yep.
get on that way.
So let's just carry on. And then the proportionality constant, as I mentioned, is introduced because the units we use for temperature and pressure are a little different, as it were. Okay, so according to this gas law, rising air cools because it expands as it enters a realm of lower pressure. An expanding gas will cool off. And I can actually have us do a little experiment to prove this. What do you do if you want to cool off a hot piece of food?
You blow on it.
Yeah, how do you blow on it, though? Pretend you've got a hot piece of food here. Okay, notice that Mike naturally is conducting the proper scientific experiment. He's actually pursed his lips so that the hole that the air comes out of is really small. You notice that? I'll do the same thing. That's how we cool off something. If we want to warm something with our breath, we go, because the heat of the air in our body is preserved that way. So how is it then that making a small opening with our breath, with the hole that the air comes out of, why does that lead to cold air? Aren't we compressing the air when we do that? So why does it lead to cold?
I think there's more pressure behind it, more volume behind it.
It's because as the air comes out of that little hole that we make with our lips, the air rapidly expands. And expanding gas causes it to cool down. So that's why when we try to cool off something, we create a situation where we're making an expanding volume of gas. We have a narrow opening, and as it expands, it cools off. Conversely, sinking air warms because it contracts as it sinks under higher pressure. And corollaries of this, a given parcel of air. So meteorologists often talk about parcels of air. A parcel of air, you can imagine a boundary, an incredibly thin mylar, infinitely stretchable or compressible boundary. Like a balloon, but even more flexible than a balloon, that holds a parcel of air. And as a parcel of air has a larger spherical shell to fill as it rises up in the Earth's atmosphere. You can see this picture on the slide where consecutive layers of the Earth's atmosphere have to go around all of the layers underneath them. So there's more volume for them to fill because the radius, right? The radius is larger. So that's one of the reasons that the pressure decreases with height is because we're on a spherical world. Another reason that the pressure decreases with height is because of the weight of the air on top of it, which I mentioned previously. So these conspire to make a fairly consistent effect where rising air expands and cools. And that is really important for the climate, and for the clients out there as well. All right, so here's an example with a little more detail behind it. This rainbow-colored line on this graph represents a region of constant pressure. And here we are over a farm field somewhere in the Midwest, as it were. And we've got this nice constant pressure overhead. Well, what happens if suddenly there's a heat source, right? Now, this would typically be a pretty large heat source, but even a small heat source can cause the same phenomena on a smaller scale. But if the heat source is large, like a body of heated water, or maybe some ground that's got a lot of stored heat in it, that it's releasing this heat at night, etc., then the air that's getting hotter must expand. So this level of constant pressure, which is what this kind of rainbow line designates, for a given pressure level, the air expands as the temperature increases near the heat source, right? Well, now that's sort of scrunched up the air on top. And you've got this rising warm air that creates a low pressure. Rising air creates low pressure. Up top, where the air is scrunched, you've got a local higher pressure area. And within all natural phenomena involving gases, including the atmosphere, you get a net flow of material, of air, from high pressure to the lower pressure region. So you get these upper level winds that go from lows towards highs.
Or
From highs towards lows, sorry. But they're going from surface lows to surface highs, okay? And the net result of that is you get this circulation. You get a circulation cell in the atmosphere that carries air in different directions at different levels. And this moving air mass between high to low pressure, on the ground, you'll notice the direction of high to low is along the ground. So along the ground, you'll feel the air moving in this image from left to right, whereas up high in the air, it goes from right to left.
It's always moving from a high area to a low area.
Right.
Because with high pressure, things want to maintain or regain the equilibrium
Right.
of even pressure.
Right. So this drives circulation tendencies within the atmosphere. So this is kind of reversed from the picture I had before, but here you see the high pressure falling down from on high, not the pressure falling down, but the air parcels are falling down from on high, moving laterally across the surface of the land or the ocean, and then rising as they're heated up. All right. Uneven heating on a round planet plus heat flows trying to even out the temperature cause this amazing thing to happen habitually in our atmosphere. This is a sort of a cross-sectional view of what are called the circulation cells that are typical in our atmosphere. If the Earth did not have a complicating factor of varying terrain and varying ocean currents, then this model, this simple model, this three-cell model, 3 cells from the equator to the northern hemisphere and 3 cells from the equator to the southern hemisphere, this 3-cell model would be nearly perfectly sufficient to describe the climate of the Earth. But we have complicating factors when we start introducing land masses that interfere both with airflow and ocean currents and whatnot. But we can still learn a lot by referring to this model. So the red line is essentially the part of the Earth where the sun is overhead in the daytime, and this corresponds to the equatorial region. You'll get equatorial heating. Hot air at the equator rises. As it rises, it cools off, and it circulates at the high levels of the atmosphere to a point where it's cooled off enough to actually start plunging back down. So wherever this cool air plunges back toward the Earth, we have a geographic, topographic feature associated with that, and we call those deserts. So as the air rises and cools off, one of the things that happen is it gets rid of, or it releases its moisture content. I'll talk more about that in a few minutes. So around the equator, we typically have a fairly constant area of storms. And this area by sailors was called the doldrums. You know, it's just always gray and rainy, and it's just hardly ever a sunny day, and that's the doldrums in our global model. And then as you move northward and the air cools off and releases its moisture, then it starts plunging towards the earth. And what happens when you get air from up above piling down? That will be increasing the pressure, so you get a high pressure. Whereas at the equator, you have low pressure because the air is wafting up. So typically, the deserts on our planet are located at these sort of 30-degree north lines, which correspond to the plunging air that has cooled off and become denser, and it's plunging towards the ground, but it's hot and devoid of moisture, it's cool and devoid of moisture, but as that air falls into an area of higher pressure, it compresses, and that heats it up again. So what started as cool winds aloft, plunging towards the ground of the desert, has instead, because it's compressing as the atmosphere gets denser near the ground, this air heats up, and it's responsible for the many of the deserts in the world. Now again, topographic features globally can also change this pattern a little bit. You can also have deserts in the, not the windward side of mountain ranges where the wind is coming towards the mountain, but the leeward side away from the wind. So as air comes up towards a mountain, it rises, it releases its moisture, and then comes down on the other side. And on the other side of mountains, as the air comes down, if it ends up falling into a region where it's particularly low topographically, then it can heat up tremendously. And this is one of the causes of something deemed the Santa Ana winds in California. The air relatively cool from the nighttime in the desert elevations come up over the Sierra Mountains and then plunge downward towards the coastal cities. And as that dry air, not terribly hot air, plunges down towards the sea level, it's compressed, and that compression adds about 10 degrees per 1,000 foot of falling. So the Santa Ana winds are a dry, hot wind. And they're not dry and hot specifically because they're from a desert, although that may be why they're dry. They're especially hot because they fall off of the mountains. And as an air parcel falls, it heats up. So here's a sort of an animated view of this same model. This indicates the seasons. So as the Earth moves around the sun, it maintains its axial tilt. Here's the sun, and the Earth maintains its axial tilt. So at some point, the northern hemisphere is pointed towards the sun, and then in the wintertime, the northern hemisphere is pointed away from the sun. So this tube of energy from the sun, the light rays, in the summertime, it may hit, at a fairly less steep angle, whereas on the other side of the sun, that angle could be changed significantly from season to season. And that's why we have our seasons. And this animated picture shows the area of maximum heating moving north and south through the seasons. Similarly, it shows these convective cells, especially the first area of cell that creates the deserts. Those are called Hadley cells. It shows the Hadley cells. And then after those cells is a smaller area, and in fact the effects of those smaller cells is typically attenuated by topographic features, but those are called feral cells. We'll get to that. I think that's the only time I'll mention these feral cells. And then at the pole, you've got these falling cold air. So you've got, whenever you have falling air, what kind of pressure do you get?
Higher pressure.
Higher pressure. So you've got typically polar highs.
Now, some of it's affected too just because of the fact that the Earth is rotating.
Right, the Coriolis effect, right? That's one of the reasons why storms, storm fronts and pressure fronts tend to bend from our perspective on the Earth, is because the Earth is imparting a Coriolis force, and that force increases in magnitude as you get closer to the poles and decreases as you get towards the equator. So here's an example, a cross-section of these cells. Again, the equatorial cell is the Hadley cell, and you've got air rising, warm air heated by the sun rising from the equator and forming storms, and then moves across a high level and then falls down and makes these deserts at 30 degrees north. These on the ocean, this corresponds to the horse latitudes. So the horse latitudes are famous for being a place where there's almost no wind, and it's clear and dry and sunny, which, if you're in a sailboat, is not very helpful. So there's different stories about why they were called the horse latitudes, including maybe throwing horses overboard or eating horses for people that are desperate because their ship isn't moving. And then a similar reverse sort of circulation happens in the next cell, which is called the feral cell. And in that cell, the band of low pressure, the ridge of low pressure delineating the edge of the cell happens to be at the northern latitudes, about 60 degrees, and that's smack dab in the middle, so to speak, of where much of civilization has built its homes, is in these temperate climates. And those temperate climates tend to have storm systems that move through, because the polar air is driving. The cold polar air is driving underneath relatively warmer air that came from the equator, and that warmer air rises up above the cold air and also causes storms. So we've got the Hadley cell, the feral cell, and the polar cell that are largely responsible for driving the large-scale factors of our
How do you
climate.
spell feral?
Ferrel. Okay. Named after a person. I forget when he lived, 1800s, I think. All right. Let's see. Well, as if my clicker isn't working here.
Oh, no.
One of those days.
Is it on?
Yeah.
Turn it off and on.
I'll turn it off and on. Good idea. All right, let's see if it works now.
Can you advance it up top? AV people?
Technical challenges seem to be the word of the day.
Yeah.
Yeah, I don't know what else to do. I've got this.
Let me see if I can.
Oh, there, it's working now. Did you do that, or did I do that? Okay, so here's a concept that's important when talking about climate. If you're talking to a meteorologist, it's called the dry adiabatic lapse rate. So what's a lapse rate? A lapse rate is a fancy word for the change in temperature with height. That's it. That's the lapse rate. It's the rate at which temperature lapses or cools off as you rise. Occasionally, in rare circumstances, you may have a region of the atmosphere where the temperature is actually heating up as you rise, and that causes a little hook in the graph of a lapse rate, and that's really indicative of storms. But in any case, the simplest lapse rate model for the atmosphere is when you have a dry parcel of air that rises, expands, and as it expands, it cools off. Similarly, or conversely, a parcel of air that sinks, compresses, and heats up. And we're assuming that there's no energy source coming into this parcel of air from anywhere else. This is just the way a parcel of air behaves due purely to pressure changes, which correspond on our round Earth to elevation changes. So this is called the dry adiabatic, so there's no water in this cell, that's important, and adiabatic means there's no energy transfer. So it's the dry adiabatic lapse rate. But rarely on our planet is it completely dry in the atmosphere. The atmosphere, if you were to take all of the water out of the atmosphere and add it as a layer of water covering the entire surface of the Earth, how thick do you think that layer of water would be?
All the humidity in the atmosphere.
Yeah, all the clouds, all the rain, everything that's locked up in the atmosphere.
10 feet?
10 feet? Good answer. Are we back on Zoom? Dave, do we have a...
Yes, but I told everyone to leave.
Oh, to go to the YouTube?
Yes.
Okay.
So finally back up.
Okay. In any case, I'm sure there are others of you out there who are having a guess as well. But Mike's, you're 10 feet. The answer is 1 whole inch.
Oh, really?
1 inch. All of the water in the atmosphere, if it were condensed out into liquid, would cover the surface of the Earth in 1 even inch of water.
So that's not how Noah's flood occurred, I guess. Huh?
Plausibly, no. No.
Okay.
Yeah, I won't even speculate about how that might have happened. So, as you know, moist air can be quite oppressive. We have this idea of relative humidity. If you've got the same amount of water in a smaller volume of air, then the air may reach its saturation point. Air has a limit. Air of a particular temperature has a limit to how much water vapor can coexist with the hot air molecules at the same time. And we can think of this as sort of the carrying capacity, the heat capacity of a parcel of air. And a small, dense parcel of air may have a particular temperature, and as that temperature is relatively cooler, it has less of a capacity to hold water vapor. If that same amount of water vapor is spread out into a larger container, then the relative humidity goes down. So generally speaking, for example, at nighttime, the same amount of humidity in the air will actually feel damper as the day progresses into night because the air cools off and decreases in size. Cooler air, remember, is less dense air. And so the relative amount of water vapor that cool air can hold goes down, which makes its relative humidity, compared to its maximum possible vapor content, the relative humidity goes up.
You said cooler air is less dense, and you went like that.
More dense, I'm sorry.
Okay.
Yeah.
Cooler air is more dense.
Right.
That makes sense, okay.
Yeah, thanks for catching that. So here's a graph, just I threw in incidentally. This is sort of relating relative humidity to temperature and where the comfort index is. The yellow is be careful because it may be a bit uncomfortable. Orange is don't exert yourself because it could lead to heat strokes and whatnot. And then the red is you need lots of water and a cooling source potentially. And for the same temperature, the amount of water evaporated in the atmosphere at a given temperature, or the relative humidity, has a profound impact on the comfort level. All right, now previously I talked about the dry adiabatic lapse rate. What happens to a parcel of air that either rises and inflates, increases in volume, or descends and compresses in volume. We had compressive heating and we had expanding cooling. Well, what happens if there's moisture in this air that is undergoing this vertical transport between lower elevation and a higher elevation in the atmosphere? Well, if you cool off air that's got a high water or water vapor content, then there's a good chance that that will incite some condensation. And the water vapor could turn into tiny little droplets. These droplets are 1/100,000th to 1/1,000,000th the size of a raindrop. Tiny little condensates of particulate water, and as they're so tiny that they easily are lofted higher or lower or vertically on the whims of the wind. So water condensation happens as warm, moist air cools. And this can cause a different lapse rate measurement, or a lapse rate standard, compared to the dry lapse rate standard, which was 10 degrees per 1,000 meters, or 10 degrees per kilometer. So this tends to be more like about 5 degrees per kilometer. It's highly variable based upon the relative humidity of the air. But in any case, the implication of that is that moist air behaves differently than dry air in terms of heat transfer. And some of the energetic heat transfer that happens in moist air happens because of water changing phases. So one of the things you'll know if you've ever gotten out of a shower, I assume most of you have at some point, is when you get out of the shower, you may feel cooler in your house, even though your house temperature hasn't changed significantly. Well, that's because the water, the liquid water on the surface of your body, is evaporating and turning into vapor. And as it does that, that consumes energy away from your body, consumes heat energy, and it cools you off. So evaporating air, air that turns from liquid into gas, absorbs energy in order to go through that phase change. Conversely, if you have water that is condensing from a vapor to a liquid at a high elevation because it's cooled off and the ability of the air to contain water diminishes, its heat capacity diminishes, its vapor capacity diminishes. Well, now you've got the opposite. Now you've got water vapor turning into liquid. And that's a heating process. So that can create a feedback system in the atmosphere where air is rising and cooling off, but as it cools off, the vapor content of that air goes through a phase change and changes into water, potentially even ice at higher elevations. And that can release energy. The phase change into water releases energy that heats up the air. Well, now it's hotter, so it rises more, and it gets to a kind of a feedback loop. And that's one of the reasons that we get storm clouds forming. Or other clouds. Not all clouds are storm clouds, obviously. But cloud formation is because the air, relatively moist air, has reached a level in the atmosphere where the pressure is low enough that it expands and cools off, and some of the water vapor condenses into droplets or snow crystals, ice crystals. And then here's a graph of environmental lapse rate. Remember, that's the real temperature change above a given point as you go higher into the sky. That's called the environmental lapse rate. That's what you would measure with a weather balloon or some other mechanism. The actual change in temperature with height, again, is the environmental lapse rate. And then you've got the dry adiabatic lapse rate, which you can think of as a slope, right? It's the amount of change over height, the change in temperature over height. Well, that's a slope, right? That's mathematically speaking, that's just a constant slope. And then you've got the moist adiabatic lapse rate, which is for air at its maximum moisture content, what happens to the temperature of a parcel of air, right? And that's a graph with a different slope. And if the environmental lapse rate, as you go up a mountain or in a hot air balloon, if the environmental lapse rate plot crosses into some of these regions on this graph relative to the dry adiabatic rate or the moist adiabatic rate, it can indicate either absolute stability or instability or conditional instability, where you might be able to get some kind of feedback mechanism going. If it's in the absolutely unstable event part of the graph, that means the air generally is more humid than the atmosphere can tolerate, and so you will have condensation and you will start getting some feedbacks that lead to the build of clouds and possibly storm. Now, from a meteorological standpoint, instability doesn't necessarily mean thunderstorms. Instability could just mean a thermal, right? Airplane going through turbulence, or an eagle soaring on a thermal. Those are localized effects where over that particular point of the ground, the environmental lapse rate is such that it's causing some local convection, and may cause some local condensation of clouds or fog, depending on how high or low it is. But that is considered unstable, not necessarily stormy, but unstable.
And most of the time, weather being what it is, with so many variables, is going to be unstable in some way.
Yeah, often, except on if you're in a high pressure system. So if you're in a high pressure system, it'll be pretty stable. The air will already be dense and not tending to rise. And generally speaking, you'll get clear, sunny days if you're in a high pressure zone. And conversely, if you're in a low pressure area, then moist air can loft aloft more easily and create clouds and storms. So if you get one of these weather stations that you can buy for your house, it can be as simple as saying, well, the tendency seems to be going towards lower pressure. That means it's likely to rain. Low pressure systems bring rain. High pressure systems bring clear days. Largely because of the relationship to this kind of graph, of the stability.
Well, you would imagine that a low pressure area would also, because it's low pressure, winds, things from other areas would be coming to fill that pressure
Right.
as well, and so then you're going to get something
Wind.
coming towards you, right?
Right. So that's one of the, so as Mike said, if you're in a low pressure area, you might expect that the surrounding high pressure areas would be driving wind towards you. And that's what we see. And then because of the Coriolis force, that wind often circulates. So we get, big looping fronts of wind. And then in extreme cases, we get cyclones and hurricanes and whatnot. Okay, so the terrain, topography, can have a big impact on the weather. One of the things I said is that as air lifts, its moisture ability to hold moisture decreases, and so you get condensation as air moves up, and then you can get, on the windward side of mountains, you can get condensation, greenery. And then on the lee side of mountains, especially a mountain range that blocks large-scale airflows, you will often get drier conditions on the lee side of mountains.
I'm thinking of eastern Oregon and Washington State and so on, and on the east side of the Sierras in California as big examples of that, and where the fires are occurring. Right. And just the topography has an impact on how dry those places are. So
exactly.
Yeah.
Yep. And then you get the Santa Ana winds coming down. If they're pushed over a mountain and fall and dry out, they can dry out vegetation on the other side of the Sierras too, and exacerbate the fire hazard potential. So, like Mike said, in the lower left corner of this, you see that if you're in a low pressure zone, air may be rushing toward that from a relatively higher pressure outside that zone, and that air rises, and as it rises, it condenses, and that's where you might get rain showers. On the other hand, you may have an area where you have some warm, like in the lower right-hand picture, where you've got warm air sandwiched between two different cold masses. And one of the things that could happen is that the warm air could ride up on top of the cooler air. And when that happens, you generally get the sort of day-long rain showers that you've all experienced in your lives sometime here in this climate, where you'll just have a gray ceiling of clouds and a constant rain and really not many storms. That's typically because warm air, typically from the west, is riding up above some cooler air, and as it rises, it condenses and forms rain shower sorts of clouds. On the other hand, if you get cold air pushing into a region where you already have warm air established, then that warm air, which is less dense, the warm air is lofted over the top of the cold air, and as it rises, you get condensation, and that's where you can create some of the big boomers, thunderstorms and whatnot. So two different types of precipitation depending upon the relationship between the movement of warm and cold air. There are differences between air, land, and sea in terms of their ability to absorb and retain heat over periods of time. Air is a relatively poor conductor of heat. In order to get heat moving from place to place in air, you pretty much have to move the air, right? It's convective flow. So still air, if you have air that's still or trapped in a region, you're not likely to get much heat transfer. Well, that's one of the reasons we use insulation in our homes that traps pockets of air. It traps that air and it keeps convective heat transfer from happening in the air, even at a microscopic level around our houses. So still air, if you can prevent air from moving, you can prevent a lot of heat transfer from happening. And that's what insulation does. Insulation just provides a lot of air pockets. Land is a better conductor of heat. So you can get thermal conductivity within the bulk of land, whether it's soil or sand or granite in mountains. Land has a better ability to absorb heat, retain heat, and then radiate that heat as infrared radiation in the nighttime. But the winner, in terms of heat capacity, is water. Water has a tremendous capacity for absorbing energy, heat energy, and storing it in the vibrational and rotational energy of the individual water molecules. And the heat capacity of water, combined with the fact that air has to move in order to try and seek equilibrium between pressure and temperature, those two effects of water, air, and the pumping of constant energy from the sun constitute the engine of our climate. The water cycle is important to our climate, right? As I said, water has an ability to store a great deal of heat energy. And one of the things that can happen if you heat up water enough is it turns into vapor. It goes through a phase change and cools off, as I said previously. Well, that cool, vapor-laden air could rise and expand and cool off even more to the point where it can no longer hold the vapor. Well, then the vapor turns into water. What happens when it does that? It releases heat energy. It releases the heat energy that originally was used to vaporize it. And some of this energy turns into the motion of these microscopic water droplets within clouds. And if you get above a certain height, then you get the formation of ices. And you get water droplets and ices bumping up against each other and creating all kinds of complex convective currents that you'll see making sort of a cauliflower shape in growing storm clouds. And then the storm clouds typically will drift over land, and if those clouds and the air masses are elevated over a mountain, that's where we'll get rain on the windward side and then dryness on the leeward side. So land, topography, ocean, water, even large lakes and water, or very dry, or very wet, inundated areas of land too can create a feedback situation where the land is evaporating water. So here's some clouds that are because of air that's lofting over a ridge of mountains, and as that air rises over the mountains, it condenses and forms these nice wispy little clouds. Then here's a chart displaying some of the types of clouds that we get. Everything from nimbostratus, which are those sort of day-long rain clouds, to the cumulonimbus, the monster clouds that cause thunderstorms and whatnot. And then different types of clouds, depending upon the altitude where they exist in the atmosphere, and the moisture content and the heat capacity, relatively speaking. So all kinds of complicated clouds. And this is just a partial list. There's all kinds of other clouds that are less common that are not shown on this chart. So one of the things that happens whenever you have a system that's deriving energy, constant influx and outflux of energy, is it tends to set up waves. This is why, for example, you have the wave equation in quantum mechanics and the wave equations in heat transfer and whatnot, is that typically when you get heat transfer happening, you'll get waving kinds of patterns. And we see this pattern in this satellite view of I believe this is moisture content of the air. And this wavy pattern, especially in the junction between the polar cell and the feral cell, that happens at temperate latitudes, creates these waves. And these waves are what we typically associate with the jet stream at high altitude. Remember, pressure differences cause temperature differences, and temperature differences cause winds. So you get these high-level winds, and you can get these fronts. To those of us who are accustomed to thinking about a flat topography of our environment, our states. You look at a map of your state, and your state looks flat. So weather maps look flat. But on the spherical Earth, this is sort of a sinusoidal wave pattern that moves around the Earth, and where air masses meet or rise and sink, you get these kinds of patterns. And it's really beautiful to watch these sorts of time-lapse. You can find these on the internet, these time-lapse displays of both airflow and moisture flow around the planet. And then this is around the South Pole. Around the South Polar region, there's fewer land masses in the way, so you can really see that circumpolar circulation around the polar regions. All right, and then one of the things that can happen is the water, especially in the north polar regions, as more water is exposed to sunlight, then that water heats up. Well, heat causes the air to rise. Rising air is low pressure, so you can get these habitual low pressure systems in Arctic regions, and those can have enough energy and wind compared to the high pressure systems around them, and then combine that with the wave-like natural action, and you get these pressure ridges. This is a polar vortex. This is a wintertime. You may have heard about this, a wintertime extension of the sort of weak low energy system coming from the north that happens to be low pressure rather than high pressure. And as cold air moves into warm air, you get this lofting of air from lower altitudes that causes these storms. Once again, to reiterate that point, these are the two kinds of storms. You can get these nice rainy days, or you can get storms, depending upon how the hot and cold air masses react to one another and move with respect to each other. Here's another view of that same thing, right? This is a really important point, that whether or not a warm front climbs above cold air or whether it's pushed out of the way by cold air has very different consequences for the kind of weather you have. Cold fronts cause storms as they push up. Warm fronts cause storms cold fronts that move into an area of warmth can loft the air. So one of the things that can happen is you can get little pieces of air that are sort of chopped off, and these are called occluded fronts. And that's the purple region where the cyclonic activity is showing up on this map, where the cold front, that's the blue arrows, and the warm front, those are the red semicircles, where those fronts meet. They can cause some swirling due to the Coriolis effect of the round Earth, and that can pinch off a low-pressure system that has a lot of circulation around it. And these are subtropical cyclones. Storm clouds. Typically, you get an updraft where the water's condensing. Eventually, the air will cool off so much that it will be able to sink. So you get a downdraft on the other side of the storm. And that's one of the reasons why if you're in front of a thunderstorm coming at you, you'll often feel a cold draft preceding the storm, is that the cold downdraft from one side of the storm. And if you've got shear forces aloft, which I'll talk about in a minute, that can cause a really powerful storm. But eventually, the cumulonimbus will dissipate. And this happens in 30 to 40 minutes. So a given cumulonimbus will build, cause rain or precipitation, and then dissipate within a period of about 40 minutes. Now, the front may not go away, and so it's continuously making new cumulonimbus. But if you get wind shear aloft pushing storms along, then it can help feed cold air into a previously warm air region, and you can get just a sort of a chain reaction, a whole storm front if you've got wind shear acting. And one of the things that shear can do, because of, again, the rotation of the Earth and the Coriolis forces, it can set up these supercell tornadoes, or not tornadoes, it's just a supercell storm, where it's a gigantic storm that can be, 100 miles across or so. And it's just one of the things that nature can do, given hot and cold air masses meeting. Can be the size of, let's see, they can form 4 types of thunderstorms. Supercell, which this is a squall line, which is kind of what I talked about previously. If you've got continuously moving air masses pushing a front, and then you can have multicell, where you've got cumulonimbus clouds sort of popping up along a ridge of pressure, or you can have a single cell. You can have a single cumulonimbus. And then here's an anatomy of a cumulonimbus cloud, showing, in this case, a supercell. And one of the things that a supercell can lead to is a tornado, where the air circulation and the low pressure becomes so pronounced and strong that it can actually reach the ground as a tornado. Here's a squall line where wind shear and strong winds are pushing a storm front forward, and this forms a derecho. We had one of those earlier this year. And then here's an image of a derecho forming. And look, notice the comma shape. That comma shape is characteristic of storm fronts over continental regions. And you can even see the occluded front, where it sort of pinches off to the northwest there and makes a cyclonic rotation as that region loses energy and begins to dissipate. Lightning. If you get ice and water particles bumping into each other, you can get some charge separation within a cumulonimbus cloud as some warm air rises and cold air falls, and the water particles or ice particles come into collision. And that charge separation can create a high voltage potential, leading to lightning. And lightning is a spectacular phenomena of weather. We get electricity out of nothing more than water, air, and sunlight. It's a witch's brew. And lightning always is associated with thunder. Some people talk about heat lightning that has no thunder. Well, that lightning is just so far away you can't hear the thunder. But all lightning causes thunder. Here's a map showing relative number of lightning strikes across the world over time. And then one of the other interesting things that can happen is in the tropical region, the Coriolis force of the Earth can spin up storm systems that feed off of the warm air of the ocean to form hurricanes. And one of the interesting things about hurricanes is that you don't typically get thunder and lightning in a hurricane. You can, if they move towards land and give rise to other cumulonimbus clouds, but the inflow of air around the low pressure of a hurricane is typically lateral, comes from the sides, rather than as much from the top and the bottom like you get in the supercells. So you don't get as much friction in those hurricane clouds as you do in other clouds in more temperate regions. So you don't see as much thunder and lightning from hurricanes, and this shows where hurricanes are prone to happen. Now, one of the things I didn't talk about, and I'm not going to talk about, I don't have the time, is the relationship between ocean circulation currents and wind currents, but that's a very important factor when talking about meteorology and predicting the weather. And it influences things like the paths of hurricanes and whatnot. La Nina and El Nino, real quick. La Nina is a high pressure system in the Pacific, and it can change the winter weather patterns as well as changing the strength and impact of hurricanes in the Atlantic. This is the influence of La Nina, and this video will be up online for you to go back and look through later. And then we also have La Nina, which is sort of the inverse pattern, where you have a low pressure in the Pacific, and that also has implications for the Atlantic hurricane activity. Typically fewer hurricanes, but then you might get more hurricanes around Baja California on the Pacific side. Biophysical feedback. If it weren't for trees transpiring, giving off moisture, there's been some estimates that all of the moisture would have been drained out of the air masses by about 400 miles inland away from the oceans. So it would be dry everywhere if it weren't for vegetation, especially trees transpiring and helping to perpetuate the availability of moisture inland. And this is a map I tried to draw showing a 400-mile boundary, and all the gray areas would be dry, desert-like, if it weren't for vegetation. So deforestation is causing problems for the climate as well. Other things that humans are doing are causing problems for the climate. Anthropogenic climate change, increasing CO2. There have been a lot of talks about climate change here over the years. I'm not going to go into detail here. This is a good chart off of Wikipedia showing some of the driving mechanisms and consequences of climate change. And this is a graph showing that the most severe climate change impacts are actually in the polar regions. So as more ice melts, more water is uncovered. Water can absorb a lot of heat. So one of the reasons we get polar vortexes more often and severe winter storms is actually because the Arctic is warming and causing those low pressure systems that can reach down and cause those polar vortexes.
I just heard that a few years back in Russia and Siberia, so much heating had occurred there that tundra that had been frozen for a few hundred years was now thawing.
Yeah.
And reindeer that had died of anthrax, where the corpses that were 100 years old were now coming up to the surface.
Thousands of years old.
I thought this was from an anthrax
Okay.
of 118 years old or something like that. But the anthrax was coming out of these, getting into the soil. The reindeer that are alive today were eating the grasses and lichens and so on that now were poisoned with anthrax that 118-year-old caribou had.
Wow.
And now herdsmen and people there were now getting anthrax that had been laying dormant for that long. You know, I know up in the north, as snow melts, darker ground
Right.
absorbs a lot
More
more
heat.
heat too. So
Right.
another reason the polar regions are gaining heat much more quickly.
Right, and releases more greenhouse gases in the form of methane.
It's a positive feedback loop that keeps on building and building and building.
Yep. Also, fires become more widespread and burn longer and further geographically, and that releases more carbon dioxide into the air as that wood is consumed. So, anthropogenic climate change is real. We have copious evidence for that, just like we have copious evidence that we live on a round planet. And our round planet and the sunlight and the land and the moisture in the air conspire to drive our weather. So that's weather in a nutshell. How about that?
I like that. That's great. One thing I think it's important to say is the difference between weather and climate. I think, we maybe didn't emphasize that so much, and how critical and important it is. People, bring snowballs onto the floor of the Senate and talk about how they don't believe in climate change because, the weather can be a certain thing. You can always have a change in weather.
Right.
But I think Neil deGrasse Tyson described weather and climate, the difference between them, as one is taking your dog for a walk on the beach, and as you're walking from one end of the beach to the other, your dog's free and off the leash and going, sniffing at the water, then going up high in the plains and everywhere it goes. But basically, through the whole course of the time, the dog is walking with you across the beach from one end to the other, but it's going thousands and thousands of steps. Yeah, your pathway that you take walking across the beach is similar to climate, while the dog's random maneuverings all over the place can be similar to weather, changing completely and being very variable, but still having a path and a pattern to it as well.
Well, like I said about the polar vortex, right? That's happening largely because of global warming. The warming of the Arctic actually diminishes the staying power, the sticking power of the cold air in the Arctic, and it begins to leak out, as it were. And that can cause polar vortexes, which cause more severe winter storms. So the idea that a severe winter storm can be because of global warming just doesn't seem intuitive, and it's not intuitive.
Right. They say global warming, but really climate change. But the planet is warming.
So
that's a problem.
If you could bring up, stick with me for a minute here, if you could bring up that interactive globe. I've got an interactive globe. I recommend that those of you who are watching this at home or subsequently online can find this website. And let's see if I can see this well enough. There's a monitor down here I think I can look at. So using this website, you can select all kinds of interesting things about pressure and temperature. One of the things I want to show you is this Antarctic, these waves of cold air around the Antarctic. These waves are less interrupted because there's less land, less land around about the 30-degree towards the equator from the South Pole. It's mostly open ocean, so you can get these vortices of air in this polar cell. Remember I talked about the Ferrel cell, the Hadley cell, and the polar cell. The polar cell is really apparent in the southern hemisphere, and you get these waves of temperature and pressure. But I really recommend this website. You can see the URL published there on your screens. It's one of the best interactive maps I've found that can show all kinds of interesting data about the state of the world and its climate in near real time. So thank you all for tuning in. I apologize for the Zoom issues. One of these episodes will have the Zoom technical problem sorted out, but I believe you've been able to see this on YouTube. Thank you for joining. Have a safe week. Stay safe at home. Learn more science. And remember, this is your science forum as well. So if you have a science topic you'd like to share with us, you can let Mike and I know, and we'll be happy to have you stand up here and share some insights with us as well. Thank you very much. Have a good day.
Great. Thanks, everyone.